Hello, today we're going to talk about how we name covalent compounds, and I'm going to give you a very brief little introduction to organic chemistry. So let me give you just a brief little review of how we classify molecules. When you are looking at a compound and you see a metal and a nonmetal, that's going to be ionic. Or if you see a polyatomic ion, that's another good clue that it's ionic, like NH4, Br, or something like that, ammonium bromide, that's ionic. So that you're going to follow the rules of naming ionic compounds. You could also see something that starts with a hydrogen, like H2S. That is also ionic, but it's specifically an acid. And so it's going to follow the rules of naming acids. Now for molecules, covalent compounds, those are the ones that have only nonmetals. So something like CO2 is covalent, only nonmetals. And it's going to follow the rules for naming covalent compounds. So let me make a little note here. For ionic, we have metal with a nonmetal or a polyatomic ion. And then you have your acids. Acids always start with hydrogen. Now another category that you might see is if you have carbon and hydrogen, and then you might have something else. And I wrote X and Y because it could be any numbers of carbons or hydrogens. Those are going to be organic compounds. If you see carbon and hydrogen and maybe something else. Frequently it could be oxygen or nitrogen or sulfur. But if you see it starting with carbon and hydrogen, then you're going to follow the rules for organic naming instead. Okay, so when you name a binary covalent compound or a binary molecule, there's certain rules to follow. You are going to use prefixes to indicate amount. With one exception. If you have only one of the first element in the compound, we don't use the prefix, except when there's only one of the first element. Then, in addition to the prefix, you are going to use the full name of the first element, whatever it is. And the second element, you change the ending to "ide." So those are your rules, and I'll give you an example here. This one's a really common example that a lot of people know, CO2. So there's only one of the first element, one carbon. We do not need a prefix because there's only one of the first element, so I can just write carbon. The second element, there are two of them. There's two of them, so I'm going to use the prefix di. And instead of writing oxygen all the way out, because it's the second element, you're going to change it to "ide." So instead of dioxygen, it's dioxide, carbon dioxide. Most people have heard of that. Let's run through the different prefixes, and you should know these. If there's only one, it's mono, but remember we don't use that on the first element. If there's two, it's di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. Sometimes we will drop the A if the element starts with a vowel. So like if you have monoxide, instead of writing monooxide, we will write monoxide and kind of combine it into just the one O. But if you were to write monooxide on your test, I probably still give you credit because it's just kind of a practice thing. You still understand the correct prefix and the correct ending. So I will be happy there. But yeah, sometimes we drop the vowel at the end depending on the element that is coming next to it. So let's run through a couple more examples. For this one, CO, the first element is carbon. There's only one of the first element. So the prefix for one is mono, but we don't use mono on the first element. The second element is oxygen. There's only one oxygen, but it's the second one, so I have to use mono. And the second one, you also change the ending to "ide", so oxide. Carbon monoxide. CO2, we talked about this. C is carbon. And because there's only one, it would be mono, but we don't use mono on the first element. Second element is oxygen. There's two of them, so I use the prefix di, and the ending changes to "ide", carbon dioxide. Now in this third example, my first element is phosphorus, but I've got two of them. Well, I have to indicate two. So diphosphorus. And then the second element is chlorine, and there's four of them. The prefix for four is tetra. And then instead of chlorine, we change the ending to chloride. Diphosphorus tetrachloride. Now let's work backwards and write the formulas from the names. In this case, I have disulfur. Prefix di means two, so I have two sulfurs. Pentafluoride. Penta means 5, and fluorine is F. S2F5. For our next example, nitrogen. Well, there's no prefix there, so that tells us that there's just one of them. One nitrogen. The second element does have the prefix mono, so we're showing just one, and one iodine, so Ni. This third example, triphosphorus. Phosphorus is P, and there's 3 of them. Heptasulfide. Sulfur is S. Hepta means 7. P3S7. Make sure that you notice when the element is first in the compound, you use the full name, and when it's the second element, you have to change the ending to "ide". Now, we talked about organic compounds having carbon, hydrogen, and sometimes some other element. But why is it carbon? So organic, really the definition of organic is a carbon-containing compound, with a few exceptions. Some people don't include like carbon monoxide, carbon dioxide. Carbon-containing compound. But why carbon? Well, carbon's super special because carbon has 4 valence electrons. And so it has the ability to form 4 covalent bonds. And it could form 4 single bonds. It could form 2 double bonds. It could form a double bond and 2 single bonds. It could form a triple bond and a single bond. It could do a lot of different things. So it's very versatile in the number of bonds that it can form with other compounds. And that makes it really useful for creating these very complex structures, which are biological molecules, or organic compounds that are very complex and sustain life. Now, hydrocarbons are compounds that only contain hydrogen and carbon. So the simplest hydrocarbon is methane, and it just has in all 4 of its spots hydrogens. That's the simplest organic compound. But you could also have things like this, which is ethene, where you have carbon and hydrogen, and there's a double bond between the carbons. Or you could have very complex, like continuing structures of these carbons and hydrogens in varying size. Hydrocarbons tend to be very nonpolar as a rule, so they tend to have a really even distribution of electrons, which means they tend to only form London dispersion forces between them, and so they tend to have pretty low melting points, pretty low boiling points. Like methane is a gas at room temperature. You'll also see them being able to be burned very easily. So things like octane is a hydrocarbon that is in gasoline, and it can be burned for fuel. Now, those structures that I just drew were structural formulas, which show all of the bonds. So let me show you a bigger one. This one is butane, which is lighter fluid. I'm going to fill in all of the hydrogens. This is a structural formula. It shows all of the bonds and all of the atoms. Structural. But the larger organic compounds become more annoying to draw all the way out, and I like to say organic chemists are lazy, so we will start doing what's called a condensed formula, where all of the hydrogens that are attached to the same carbon, it's like all three of these, are attached to that carbon. I'm going to write it next to it. So the N carbon has 3 hydrogens. The next carbon has 2 hydrogens. The next carbon has 2 hydrogens. And the last carbon has 3 hydrogens again. This would be a condensed formula. Sometimes we'll condense it even further. When you have something that repeats, you would say CH3, CH2, 2, CH3. Either of those would be considered condensed formulas. That still give us an idea of how they're hooked together, but does not show every single bond drawn out. Now, sometimes you will also see skeleton structures, and these ones are fun. So let me draw that butane again, so you guys can see it. Butane is C4H10. So let me fill in all 10 hydrogens. And again, this is the structural formula showing all of the bonds and all of the atoms. But because organic compounds, it's always carbon and hydrogen. Organic chemists developed a way to draw organic molecules without actually writing C and H a bajillion times. So what we would do then is we would draw what's called a skeletal structure. So you'd have your end carbon, your next carbon, middle carbon, end carbon. And I know that just looks like a zigzag line, and that's okay. Every time you have an end of a line, that's a carbon atom. Every time you have a bend in the line or an intersection, that's a carbon. That's a carbon. And the end of a line is a carbon. And then we know that carbon can form 4 bonds. So you'd have to fill in, to get up to 4, the additional hydrogens. And with enough practice, organic chemists can just kind of do this in their heads. But this is the skeletal structure. And that's all they have to draw to mean the same thing as this. I'll give you another example. If I have something like cyclohexane. Cyclohexane looks like this, and each carbon has 2 hydrogens. I'll draw the full structural formula for this. This is cyclohexane. Each carbon has 4 bonds, so it winds up being C6H12. But what's cool about this is that we can just represent this with a hexagon, because each intersection there is a carbon, and we know that each carbon needs 2 more bonds to give it 4 total. So this is the same as this, which you get some really interesting compounds and shapes when you're drawing. Now, there's 3 kind of general categories of organic compounds that are known as the alkanes, alkenes, alkynes. Alkanes have only single bonds. Only single bonds between the carbons. Alkenes have at least 1 double bond. And alkynes have at least 1 triple bond. And the type of bond that is present in the compound can help determine what kinds of chemical reactions it can undergo. But that's what those 3 words mean. Alkanes have only single, alkenes have at least 1 double bond, and alkynes have at least 1 triple bond. Now, attached to organic compounds could be other atoms, frequently oxygen, nitrogen, sulfur, phosphorus. There are others. But how they are attached can make a difference as to how they react. And so we have these groups that are called functional groups. that are groups of atoms that are attached to an organic compound that change the way it reacts. So they have different types of reactions and properties based on their structure. So I'm going to give you a few examples here. Properties, let me write this a little neater. Properties, there we go. And some of these are going to sound very familiar to you. So if you have an OH attached to your organic compound, these are called alcohols. They could be things like ethanol, which is like an additive for gasoline. It's used as like a renewable energy source. It's also present in alcoholic beverages. There are things like rubbing alcohol. It's another type of alcohol group. Okay. You can also have nitrogen and H2 attached. These are called amines. These tend to be your organic bases. So, you have acids and bases. Amines tend to be more basic. And they are present in amino acids, which build up proteins. So they're a very important functional group there. The other kind of portion of that is if you have if one of your carbons has a double bond O and an OH, that's called a carboxylic acid. Carboxylic acid, which is acidic. And if you have both an amine group and a carboxylic acid group on the same organic compound, then it's an amino acid. But it's also in things like vinegar is an organic acid. Right? Another one would be if I have a carbon with a double bond oxygen and a hydrogen attached to it. This is called an aldehyde. Aldehydes are in a lot of different compounds, but one that's kind of famous is formaldehyde, which is also called methanol, but which is a preservative that they used to use for organic specimen. So there's an aldehyde. And notice the difference here. We've got the C double bond O, but this one's attached to an OH, and this one's attached to an H. And then if you have in your compound the carbon with a double bond O, but it's somewhere in the middle of a compound. Now notice I'm putting these like open-ended lines. That means it's attached to some amount of carbons. We don't know, whatever it's attached to, some organic compound. And so you'd have a carbon here. This next one would have carbons on both sides. So somewhere in the middle of the compound, we call it a ketone. And it makes the organic compound slightly polar. And so things like acetone, which is nail polish remover, helps it be a really good organic solvent. Alrighty. Another, and our last one that we're going to talk about here is called an ester. So if you have a C double bond O in the middle of a compound, but it also has an oxygen, like with carbons on either sides, this would be called an ester. And esters are cool because they tend to be really smelly, which can be a good thing or a bad thing, but they can be used for perfumes or like intentionally changing the smell or occasionally the flavor of different products. So esters tend to be smelly. So these things could be attached to whatever organic compound, and they change the way that it reacts or the types of properties that it has based on that structure. Now, I just want to review the terms polymer and monomer really quick. Monomer is like the single unit, and the polymer would have multiple stuck together. And organic compounds definitely form these big polymers. And a good example of that would be like amino acids as your monomer, which we just talked about. If you have your amine group on one side and your acid group on the other side, and then I have, something else might be attached to it, whatever it is. It can react with another amino acid, like this, and whatever side chain is attached to that. And they can actually come together, release water, and form a new covalent bond. So it winds up this H, we have a new bond here, like this. It's a really long one, but the water gets released and you have this new covalent bond. And really, it's like this. Like that. And so that's a peptide bond, and you can keep doing that over and over and over again and build up these really long chains of amino acids, and that becomes a protein. This is just one example. You don't have to memorize how to do this. Let me draw it a little bit nicer so you can see this hydrogen, this oxygen. Those two things come together to form water and create the new bond. But I just wanted to show you again how the monomers can build up and form covalent bonds between them to create different polymers. And amino acids turning into proteins is one example. Sugars turning into carbohydrates is an example. Nucleotides turning into DNA or RNA is an example. So this has a huge number of application in biological sciences. Now, organic compounds have their own system of naming, and we're not going to get into all of the details in this class, but there's a few things that we will talk about, and one of those is the organic prefixes, which are based off of the number of carbons. So the first thing to do would be to count the number of carbon atoms. Everything is carbon-based. So if there's 1 carbon, the prefix is meth. 2 carbons, the prefix is eth. 3 carbons, the prefix is prop. Don't say prop, it sounds silly. 4, the prefix for 4 carbons would be bute. Don't say but. It's like bute, like butane. The prefix for 5 is pent. The prefix for 6 is hex. 7 is hept. 8 is oct. 9 is non. 10 is dec. So really the only ones that are different are these first 4. Things like methane, ethane, propane, butane. Those ones are different, but the other ones should be your standard for 5, 6, 7, 8, 9, 10. Alrighty. This is based off of the number of carbon atoms. So how can we actually name these alkanes, alkenes, and alkynes? Now remember, alkanes have only single bonds. So if you have an alkane that only has single bonds, the name ends in ane. Alkenes have at least 1 double bond, and their names end in ene. And alkynes have at least 1 triple bond, and their names end in ine. So let me give you an example. If I have something like this, and so I have to count the carbons first. There are 3 carbons, so the prefix for 3 carbons is prop. And there are single bonds between the carbons, so it's going to end in ane. This is propane. Let's do another one. If I have this compound here, and then let me fill in the hydrogens. Like this, okay? I have 3 carbons again, so my prefix is still prop, but I have a double bond. That double bond makes the name end in ene, propene. And then if I have a triple bond, let me draw it up here. Let's pick a different one. Like this, we'll do it like that. Actually, let's just do 2, just to make it a little different. So 2 carbons. 2 carbons, we use the prefix eth for 2 carbons. And it has a triple bond. Triple bonds use the ending ine. So this is ethyne when you put it all together. Now, organic compounds with functional groups also have different names because of those functional groups, and you should be able to recognize it just based off of usually the suffix. So alcohols, which are OH, alcohols, their names end in all, like the word alcohol. So a good one would be like propanol. We know it is an alcohol because it ends in all. We also know it has 3 carbons and single bonds between them, propanol. If we have an NH2 group somewhere in there, which is called an amine, it actually has the word amine in there somewhere, like methylamine. We know it has a single carbon group with an amino and an NH2 group attached to it. Carboxylic acids, which are those C double bond O, OH. These are your carboxylic acids. These ones end in oic acid. A good example would be butanoic acid. So 4 carbons, single bonds, carboxylic acid group. Ketones have that C double bond O in the center. It's a ketone. Ketones end in the suffix -one. So a good example would be propanone. That is the official name for acetone. Acetone is a common name for it, but it still ends in -one. But propanone, 3 carbons, single bonds, ketone. 2 more. If I have that C double bond O with an H, it's an aldehyde. Aldehydes end in -al. So like we said, formaldehyde, but the official name for that would be methanal nowadays. Methanal. So we have that Al at the end, indicating it has an aldehyde group. And then our esters, C double bond O with another O in the middle of a compound is an ester. And esters have O8 somewhere in the name. It should be at the end of the name. So like we might have ethyl methanoate would be an example. So if you see on like packaging something ending in O8, it's going to be an ester, and it's probably going to provide some kind of flavor or smell enhancement. And so just being able to recognize the names of the functional groups. You don't have to be able to write the whole name on your own. That's beyond the scope of this class. But just recognizing some of these suffixes to say like what type of functional group would be a great idea.